extending things a little bit. Now we're going to do an extension. We're going to do some trigonometry, but it's probably not trigonometry you're real familiar with. So we're going to base all this on Euler's identity. Euler's identity says that e to the I theta equals cosine theta plus I sine theta. Now that's kind of looks weird. I is the square root of -1. In engineering, often you use J instead of I. But I stands for imaginary number, square root of -1. Okay? And this follows really very simply if you understand Taylor series. The Taylor series for e to the I theta turns out to be equal to the Taylor series for cosine theta plus I times the Taylor series for sine theta. So if you know what the Taylor series is for e to the x and for cosine x and sine x, you can very easily prove the Euler identity based on just what you learned in first year calculus. And hopefully you did learn about Taylor series in first year calculus. These functions are three of the easiest functions to which you can apply the Taylor expansion. So this is really very elementary. Okay? But it has wonderful implications, especially for engineering, okay, for mechanics and for analysis of electrical circuits and so forth. Okay, well, so to apply this identity, let's go back to the equation x double prime equals negative k over mx, which applies to any mass subject to linear restoring net force. So net force, which is a linear restoring force. Okay, so we take this and we use this as the form of our solution because we know, well, we don't know. We'll get to it. This implies, substituting this in here, that c squared is negative k over m. Now, immediately we're into the realm of imaginary numbers because k and m are both positive, so negative k over m is negative. So that c squared equals negative k over m has solution c equals I times square root of k over m, which is I omega. Now actually c could be plus or minus this, so we could have plus or minus I omega, but that's not really going to add any significant information to what we're going to get here. So this means that x equals d times e to substituting I omega for c, e to the I omega t. And what's e to the I omega t? By Euler's identity, if we replace theta by omega t, we get cosine of omega t and I sine of omega t. So this becomes d times the quantity cosine of omega t plus I sine of omega t. Now, d is not, we're into the realm of complex and imaginary numbers. There's no reason to suppose that d is a real number. Okay, this isn't a real number, so why should we restrict d to being a real number? There's no justification at all for restricting d to be a real number. So we're going to let d be a complex number, and we're going to call the real part p, the imaginary part q. So d is p plus iq. So that this solution will have the form you see here. X equals p plus iq, replacing d, and then times cosine of omega t plus I sine of omega t that we had already. We easily multiply this out, and you should really do these steps before you see me point to the next one. Do them in your head, do them on paper. On paper is kind of recommended because it really reinforces something that's going to be very important to you. Okay? And so multiplying this out, we're going to have a p times the cosine of omega t, and an iq times I sine omega t is going to give us I squared sine omega t. That's going to be I squared times q sine omega t. That's going to be negative q sine omega t, since I squared is equal to -1. And we get this real part to this expression. Okay? And then we get the imaginary part. iq times cosine omega t, well, there's your q cosine omega t with an I coefficient. And p I sine omega t. There's your p sine omega t with the I coefficient. Now this is profound and extremely important. This real part is a solution to the equation. And this imaginary part is a solution to the equation. P and Q can be any numbers, so that what we have here is P cosine omega t minus Q sine omega t being a solution, and Q cosine omega t plus P sine omega t being a solution. Using either one of these as a solution, we get the general form of the solution. Instead of P and Q, I really probably would have been better off using A and B, which is somewhat more familiar. So I'm going to digress a second and do that. Okay, that's a little messy. I was in a mindset. Let's get down here where we can see what I just wrote. I was in a mindset where I didn't want to use A for the coefficient here because I knew it was going to come up later. So I just continued avoiding it, and I used P and Q here for want of better letters. A and B are better letters to use here. And just replacing the P's and Q's by A and B, we get this, and this alone is a solution to the equation. And turns out that this alone is a solution to the equation, and it's very easy to verify that. You should plug this into the equation and verify it, and you should plug this into the equation and verify it. Now, our general solution, our general real solution, assuming that A and B are real numbers, is going to be, well, let's use this one here. It's going to be x of t equals A cosine, not sine, plus B sine of omega t. And that's a complete justification of the solution that I gave earlier. Now, I haven't proved that this is the only possible solution. It is, but that takes a little more work. You really have to get a little bit into the theory of differential equations, and that's beyond the scope of this calculus-based course. So there's our general real solution. Now, I claimed that this solution can be put in the form C sine of omega t plus theta naught, or C cosine of omega t plus theta naught. I haven't proved this. I'm going to use Euler's identity to derive the trigonometric identities we need to rearrange this as either this form or this form.